Next, we look at the synchronization challenges in distributed systems and how this will apply to design and architecture of blockchain applications. Data and databases very much behave like organizations when it comes to centralized versus decentralized comparison. So let us look at the organization structures first. In a centralized organization structure, primary decisions are made by a central authority. That could be a person or group of persons at the top of organization hierarchy. The advantages are extremely efficient regarding business decisions, effective in very small organizations, whereas the disadvantages are negative effects of several layers of bureaucracy and sluggish business operations. In a decentralized organization structure, the decision-making authority is delegated throughout the organization. Advantages are a broad-based management team helps to ensure the company has knowledgeable people to handle various types of business situations. Disadvantages are decentralized organizations can struggle with multiple individuals having different opinions on a particular business decision. As such, these businesses can face difficulties trying to get everyone on the same page when making decisions. Now, let us apply the above explanation to centralized and decentralized systems. As the name suggests, centralized systems are single server based and managing atomicity of data or transaction is easy. So, what is atomicity? It means that you either commit to the entirety of the transaction occurring or having no transactions at all. Simply put, whenever data is being added, written, updated, or deleted, or for that matter, any operation that changes the state of the database is being carried out. The operation needs to be managed in a manner so that all users of the database at that moment get to see a single state. A transaction is seen as or treated as one atomic unit. If it happens completely or does not happen at all. Do we see an issue here or a challenge when it comes to maintaining atomicity in distributed databases? In fact, why just atomicity? All database properties, namely atomicity, consistency, isolation, and durability, or ACID in short. The answer is yes, a big yes. We already know about atomicity. Consistency. It ensures that the database is always in a consistent internal state. For example, in the case of tables with secondary indexes, the primary table and all the index tables should be consistent after an update. Isolation. It determines how and when changes made by one transaction become visible to the other. Durability. It ensures that the results of the transaction are permanently stored in the system. The modifications must persist even in case of power loss or system failures. In a centralized database, to achieve ACID properties is easy as the focus is on just one central server. But in case of decentralized systems, it is achieved through something called distributed ACID. In auto-sharded distributed databases, for example, databases like YugaByteDB, Google Cloud Spanner, shards are spread across multiple nodes by design on cluster creation. By auto-sharded distributed databases, we mean to say a database that has been broken up into smaller chunks that are spread across multiple servers. Coming back to distributed ACID, a transaction that impacts A set of row distributed across shards on multiple nodes is called a distributed asset transaction. Implementing distributed asset transactions in a scale-out databases requires the use of transaction manager that can coordinate the various operations and then commit or roll back the transaction as needed. Let us see how it is carried out. The goal is to serve distributed transactions with high performance and without compromises to correctness. Step 1. The transaction manager has to manage the entire life cycle of the transaction, meaning from the moment the transaction is initiated until the transaction is committed. Important to note that the transaction manager runs on each node. The transaction manager route incoming transactions to any node. Step 2. Create an entry in transaction status table as the transaction needs to be tracked in a reliable and fault-tolerant manner. The following information is stored as a part of this transaction entry. Transaction ID, which is a UUID that uniquely identifies the transaction. Status, which can be one of pending, committed, or aborted. All transactions start out in the pending status and progress to the committed or aborted status in which they remain permanently until cleaned up. Commit hybrid timestamp, which is the commit timestamp for the transaction. This is the final timestamp used for multi-version concurrency control, also called MVCC, to serve the various updates made by the transaction if it gets committed. List of IDs. These are of participating tablets, which are the final set of tablets that the transaction has written to. Read more about this in step 6, which describes how provisional rights are cleaned up. Step 3. Write the provisional records. We are still at the point of transaction lifecycle where it is not possible to predict if any of the updates will conflict with the updates of another transaction. Therefore, a need to write the provisional record, and it is provisional because it is still not visible to other users until the transaction is committed. Step 4. Here we need to understand two processes. First, manage any conflict. When multiple transactions run concurrently, they may try to update the same set of keys. When this happens, there is a likelihood that these updates might violate the isolation guarantees of the running transaction unless conflicts are detected and handled. Second, commit the transaction. Once the transaction manager has successfully written all the provisional records, it proceeds to commit the transaction. The commit operation will only succeed if the transaction has not yet been aborted due to any conflicts. Step 5. Once the transaction has been committed, the transaction manager acknowledges back to the client that the transaction was successful. Step 6. Once the transaction is committed, the provisional records are cleaned up. One important point to note is that there are many techniques and tools available to manage performance in distributed transactions. What are they? Cache transactions. Transactions when in progress to make the lookups very fast and efficient. Transaction locking to manage conflicts. Save time. Every read request is assigned a particular hybrid time, known as the read hybrid timestamp. This allows write operations to the same set of keys to happen in parallel with reads, ensuring high performance. And last, auto-detect and optimize single row asset versus distributed asset.